All right. So, thank you to the organizers for giving me a chance to talk about something that may have confused and surprised quite a few people. I don't know how many people saw that coming. And Nobel Prize in Physics for AI. Well, as we'll see, it was indeed a long time coming. The relationship between these two fields, physics and artificial intelligence, has been getting more and more intense, dare I say more and more intimate, over quite a while. And you can judge for yourself whether this is a better story than Twilight. I don't know. Okay, so here are our two Nobel Prize winners. First is John Hopfield, who is a physicist, a theoretical physicist, which means that he develops theories, usually very complex mathematical theories, to explain and describe natural phenomena. And it was while he was doing research in some very maybe interesting to physicists, but not so interesting to anybody else, phenomena that he made advances in artificial intelligence that became interesting to everybody else. So he's known for Hopfield networks, associative memory. These are things that I'll get into. The second person, Geoffrey Hinton, on the other hand, is not a physicist. He's a computer scientist, never once probably wrote a physics paper, never went to a physics conference. Nevertheless, you don't get a Nobel Prize in Physics for no reason. You get a Nobel Prize in Physics because enough physicists nominate you for one. So considering how many professors in physics decided to nominate a computer scientist completely outside their community for the greatest prize, the greatest recognition in the field, is really revealing of the obsession that so much of our community has with artificial intelligence. As someone from a physics background, I'm not a computer scientist. I'm not going to be telling you about Boltzmann machines and backpropagation. You probably don't need to hear that from me. I will be talking about the deep learning revolution in physics, which is what Geoffrey Hinton's work sparked. And I'll be talking about Hopfield's work in some detail because I think it might be interesting to many of you who work with machine learning models on a daily basis to go back in time to the early 80s, to a time when neural networks were still young. It was early days, and there was this transfer of knowledge and ideas from one of the hard sciences, from natural phenomena. These ideas then embedded themselves into the whole machinery of neural networks and have had an influence downstream. So this is maybe a perspective on what you currently do that you may not have seen before. So what was Hopfield's contribution? What was his seminal discovery? At the time when he was developing his idea of the Hopfield network, what we now call the Hopfield network, he was working in magnetism. Now, I don't know how many of you think about magnets on a daily basis. Obviously very important to most of you. One person will admit to it. Okay, not many, at least not yet. But what if I told you that magnetism and artificial intelligence were basically made for each other? They are profoundly, profoundly connected. Magnetism, as we understand it in the modern world, is self-organization. And considering how long magnets have been around, this is a remarkably recent discovery. For most of human history, it wasn't known. This thing that we have used for so many years, we didn't really know how it worked. We have to go down to the atomic level. So everything is made of atoms. And in some materials, the atoms basically form like something like a periodic structure, an array. And in some materials, each of these atoms is like a microscopic magnet itself. Now, I'm not here to teach you physics, so don't go rushing for the exits just yet. For us, for the purpose of this talk, an atom is just a circle with a little arrow in it. Okay, it's very simple to visualize. That's about as complicated the physics is going to get in this talk. But each atom has, these little arrows, and imagine them like the needle in a compass. They point in the direction of some magnetic field, which is actually intrinsic to the atom. And in some cases, they can all be independent. So they're statistically random, right? On average, there's no preferred direction, and a system like this is not magnetic. But if you can get enough of them to all line up in the same direction, then their magnetic fields don't all cancel out, and now you have something that has magnetic properties. You have a piece of magnetic material. This comes about because they all, look, enough of them kind of line up. The reason why this happens is because the atoms interact with each other. They form a network where information flows, and each atom can influence the other atoms. Hopfield realized that this flow of information through a network of atomic atoms is basically identical to the way information propagates through a neural network. And so magnets and magnetism is actually a form of artificial intelligence, with at least many of the current models of physical models of magnets and many materials. You can describe a magnet as an AI, which is quite astounding. Now, I could stand here and say magnetism equals AI and wave my hands and say words, but then this talk would be no better than a LinkedIn post. So I think I might give you an illustration, just an extended picture that will be very, very easy to follow, I promise you. We're going to imagine a very simple system, just 8 atoms, which are 8 circles with little arrows in them. But to make it even simpler, let's say the arrows can only point in 2 directions, right? This is cool because we're all familiar with binary logic, hopefully. So I'm going to replace the arrows with just numbers, plus or minus. It's more convenient to use numbers than directions. And imagine that this array of atoms is just random. So each atom decides randomly whether it be plus or minus. If this is how the array begins, what happens if you start to allow them to influence each other? What if one atom can interact with its neighbor? Well, we can create a system to describe how the state of this array might change in time. And there's a very simple version of this, right? Basically, we just look at them one by one, and each atom is going to update its state individually based on what it sees around it. So you take an atom, you look at what the states are in its neighbors, and then you add them together, right? And if the sum of the states of the neighbors is positive, then you update that atom to being in the positive state. Okay, let's put that back. If the neighboring states are negative, and you add them, so you get a -1, that's a -2. If it's negative, then the state becomes a minus, right? So what's happened is you've got an atom which is surrounded by 2 atoms which are the same state, and those 2 atoms are like bullies. They force the atom in the middle to possibly change to conform to what they are. One last situation is if they add to 0, if the 2 atoms on either side add to 0, then it's a tie. To make things really simple, even though they can get quite complicated, we're just going to default that to a plus. So that becomes a plus because that was the sum to 0, and then it. So anyways, you get the idea. If you keep doing this, eventually everything will become plus. That's just because with these rules, every atom kind of they all behave like bullies, right? They all want to enforce conformity. So we've started off with something that was totally random, and allowing them to interact with each other, they end up in this totally ordered state, right? Which means that their magnetic fields are all lined up, and now this thing is a magnet. And once you're in this state, this is stable. The system doesn't change anymore, right? Because if you take any of these atoms, its neighbors are both plus, and therefore you have to update the state to a plus. Anyways, so this, you can all see why this is stable, right? Does this make sense? Okay. What about this? Is this also stable? That's also stable. Yeah, that's kind of obvious. Okay, so this is just a basic example of a very simple network that you can start off in some random state, and the system, because of the way the atoms interact with each other, it will stabilize into one of these ordered states. Okay, this is obviously not the end of the story. We have to introduce artificial intelligence somehow. And you do that by allowing more connections. So what if each atom doesn't just interact with its neighbors, but with all the other atoms in the network? But if two atoms are farther away, then they might interact less. So now you have to start adding numbers which quantify the level of interaction or connection between two atoms. And one last thing is, because these states are essentially directions corresponding to some magnetic field, if you take a fridge magnet or something and you put it next to the thing, then the fridge magnet will also kind of move things around. But if you're an atom that's closer to the magnet, the external magnet, you might get disturbed a bit more than, you know, things that are farther away. So you need to add extra numbers which describe the external magnetic field. Okay, so now we have these new rules where you have to, in order to update the state of each atom, you have to look at the states of all the other atoms. You multiply it by the interaction, and then you have to add the external magnetic field, and then you'll just get some number like 1.6, and because the atoms are binary, you have to encapsulate this in a function which returns either plus or minus 1. Now, if you haven't totally zoned out by now, and I'm sorry for bringing equations into it, but there's a reason why I brought an equation into it. Does anyone maybe recognize this from somewhere? I don't know. What could this be? It's a perceptron, right? So the atoms are mathematically identical to perceptrons in a neural network. The way information propagates in order to create self-organization is the same way information propagates through a neural network, right? So if you want the full correspondence, the atoms are neurons, the magnetic state, the direction, is the neuron state, the activation state, whether it's on or off. What we call the interaction between these little atomic magnets are the weights of the neural network, and the external magnetic field are the biases. And finally, you have this activation function, which we call F, which in physics is related to temperature, but I won't get into this. So anyways, that's the foundational statement. This is the explanation, essentially, or the illustration for why we can describe magnets, most magnetic systems, as a kind of artificial intelligence. But the story doesn't end here. I have to tell you what came next, because that's actually quite interesting. So this whole description of information like propagating through the magnet like a neural network, it's not really that interesting if you're talking about something that stabilizes in a purely homogeneous state. Like this, it's really an extremely oversimplified version of a magnet, but you know, it's kind of some form of magnetism. There's another thing that I have to mention very quickly, which is called a spin glass. Now, how many of you have heard of a spin glass? You will never have to hear about them again, I promise you. A spin glass, I have to mention this because it's so important to Hopfield's work and to the reason why he won the Nobel Prize. Spin glasses are things that you can start off in a disordered state, and then they'll relax and then they'll stabilize, but they'll end up stabilizing and freezing in another state that's also disordered. So it'll evolve, and eventually it'll just stop evolving into some like random pattern. So it's like the system, and these are real physical systems that people do experiments on. It's like these systems, or these lattices, have these secret patterns that nobody knows. But if you start the system off in some random state, it'll decide on the closest pattern that matches that state, and it'll just settle and freeze into that state. That's called a spin glass. They're kind of fascinating for people who study spin glasses and nobody else, pretty much. But they're a stepping stone to something that's very important in the history of artificial intelligence, which is called associative memory. Because what if you could decide on what pattern the network will stabilize in? What if you decide, I have 5 patterns, and I'm going to program the network so that it will always stabilize in one of these 5 patterns, and no matter what state I begin the network in, it'll always find one of these 5 patterns that will most closely match the network, and that's how I program it. Right, so you can imagine the initial state of the network to be some sort of an input, right, which is in the modern conception of neural networks, that would be the input layer, the first, where the information starts to flow into the network. And what it relaxes into, what it ends up stabilizing and freezing in, could be the output. And now if you have 5 or 10 or 20 or 2 patterns that you've forced the network to memorize, and then you give it an input and you say, give me the closest pattern that matches this input. Does this maybe remind anyone of something? This is just a kind of image classification. It's an image classification algorithm that existed before backpropagation, before supervised learning was even, anybody even thought of supervised learning. So this is associative memory. Okay, so that is pretty much my summary of Hopfield's work. I know it was kind of maybe a bit heavy, but I think we made a few stops along the way that people kind of recognized from what they know from machine learning. What was the impact on physics? Why was this worth a Nobel Prize? Well, at the time, this had an impact on the field of spin glasses, but that was pretty much it. And outside of this kind of niche field of physics, it wasn't really that useful, I have to say. But what was the influence outside of physics? Well, Hopfield didn't just prove that magnets are neural networks. He came up with the idea of having, in a feed-forward network, you have a bunch of layers and information propagates from one layer to the next layer to the next layer. The first layer is the input, the last layer is the output. In this case, you have essentially the same layer that's copied, and each copy represents a different point in time. So this is now a neural network where the interaction between layers is actually a self-interaction that drives the network forward in time. And now you have a way of describing or modeling sequential data. So with further work from Hinton and Jan LeCun and others, this evolved into recurrent neural networks, which then became LSTMs. And for a while, as many of you know, LSTMs were the dominant way of modeling language, right? In the days before GPT and transformers, in the 2010s, LSTMs were basically the main paradigm that came before what we have now with language models. So this is kind of remarkable. We've got a physicist who no other physicists really cared about, but his developments ended up finding their way into large language models. And it's no coincidence that this came like 2 years after ChatGPT. So yeah, this is basically the story of how a physicist whose work that didn't have that much of an impact on physics ended up winning a Nobel Prize in physics for work in artificial intelligence. Now, I'm going to skip over backpropagation and everything, but the last couple of slides are just going to be about the deep learning revolution and how it works in physics. Now, if you're absolutely new to neural networks and machine learning and you don't know what supervised learning is, I'm not going to explain it, just look at the slide. But an example of how this works in physics, in astronomy, perhaps, you have an image which can be, I don't know, like an optical or X-ray or whatever telescope image. You feed it into the neural network and you want to know, is this a star? Is it a star, a planet, a black hole, and so on? How do you create a neural network that does this? Well, you need training data, which means that you need to have a bunch of images, millions of images of stars that someone has gone through and labeled and said, oh, this is a star, this is a planet, this is a black hole, right? So you've got a bunch of data from whatever, astronomy, from astrophysics, that's been analyzed using existing methods, existing scientific methods, and identified. And this picture could be also like in experimental particle physics. You could have data from a particle collider, and you want to know, is this the Higgs boson? Is this some new exotic state of nuclear matter? Blah, blah, blah. Well, that's basically what most physicists do if they're in a data-intense field. That's all they do. They get observations, they get data, they sit down and they use their techniques, their advanced scientific techniques, to label the data. And this is basically the process of creating training data for a neural network. If you were going to get a neural network to replace you, to do your job, well, you spent your entire career basically creating training data to do that, right? So this is obviously a very, very basic, simple example. I'm not even sure, I just came up with this like off the top of my head. I'm not an astrologer, astronomer, I'm not an astrophysicist. So I can't, but obviously the real examples are far, far more complex. But you get the idea, right? This is in the data intense, in more of the data intense fields. And I have to show you this data. This is from a repository of scientific publications called the Archive, which is where almost every physics paper published in the past 30 years is collected. And if you look at 4 different domains, so astrophysics, condensed matter physics, that's what Hopfield was working in, magnetism and various other things, superconductors, superfluids. High energy experiment, which is what they do at particle colliders like CERN. And then you have the high energy theorists, which are like the string theorists and basically just the string theorists. This is a plot of the fraction of papers that appear in the archive which have the words machine learning or neural network in the abstract. If it's in the abstract, it means that it's a main focus of the paper. It means the paper is about that topic. It doesn't just mean, oh, somebody used a neural network to help them process the data. It means that this paper does an actively advances advances the state of research in machine learning or neural networks and its application to physics. So this is data over the past 10 years. So 2015, if you look at astrophysics, 10 years ago, less than like 0.5% of all papers in astrophysics talked about machine learning and neural networks. And now it's up to like about 0.03. Now, you may not think 3% is that much, but that's 1 in every 30 scientific papers in astrophysics where the research focuses on machine learning and neural networks. Right. You have something similar with condensed matter physics, except here machine learning is a bit higher. There are a few more papers about machine learning, and the reason for that is because for some reason a lot of people in condensed matter physics are also obsessed with classical ML models, so like the Bayesian models and regression and so on. Weirdos, if you ask me. High energy, the experimental high energy people are also kind of in love with neural networks. Look, 7.07, that's like 1 in every 14 papers. And again, not just using neural networks, but advancing the field. Okay, so I mean, this is the trend. It's incredibly exciting, and this is basically why Hinton got the Nobel Prize for supervised learning and backpropagation, because very soon everybody is going to be using it. Okay, so I've explained the deep learning revolution and some of these data-intense fields where you can imagine machine learning models will be very useful, you know, astrophysics, all the data from telescopes, particle colliders, and so on. But what about the theoretical side? Now, that's what I'm going to talk about in the last 5 minutes that I have. What does a theoretical physicist do? Well, all modern theoretical physicists basically work in response to experiments. In an experiment, you conduct something in the lab many times with different parameters. And the experiment will give you a different outcome for each set of parameters. And then the job of a theoretical physicist is to build a model that recognizes the pattern that connects the experimental parameters to the outcomes and makes a prediction. Now, there are a couple of things that a theoretical model needs to be in order to be a good model. First of all, it needs to match existing theoretical existing outcomes. It has to match the data that's already been published and collected, and it has to be a very good predictor of future experiments. You publish a theory, someone has to do the experiment and potentially disprove your theory. If the theory is good, then it has predictive power. But that's not where it ends. There's one more thing. A theory has to be simpler than the phenomenon that you're studying, right? An example is life from biology. Life is extraordinarily complex. Natural selection is extraordinarily simple. If the explanation is simple, but the phenomenon is complex, that's called explanatory power. If a scientific model is very good at predicting things, but it's just as complex as the phenomenon itself, we refer to it as a simulation. It's not a model. Right, so theoretical physicists have to go through a ton of training, and it's decades of research experience and textbook knowledge, and teaching things and giving conference presentations, blah blah blah, in order to develop the skill of recognizing the patterns that match the experimental parameters to the predicted outcomes. What if you could conceptualize this job as a machine learning model, right? What if you use the top thing, the experiment, as a case of supervised learning? The experiment gives you essentially training data, and then you just use a machine learning model to create your theory. That's basically what theoretical physicists have been doing. Does it work? Well, we know with supervised learning, the idea is you create a model that specifically matches existing data. We know that machine learning models are good at generalizing, so they have predictive power. But are machine learning models simpler than a phenomenon study? Are they able to explain anything? Well, okay, this is going to be my last slide. We know that simple machine learning models can be more accurate, which is why machine learning models sometimes it's preferable to have fewer parameters. So that's why we have things like dimensionality reduction, feature selection, statistical regularization. This is going in the right direction if you want a machine learning model to replace a theoretical physicist. If you have a model with a few parameters that's not too complex, it has a good chance of actually explaining what's going on, giving you some intuition, and not just being a black box that can predict things but doesn't actually help you understand anything. However, we also know that more complex models can be even more accurate, right? In deep learning, we know that models with billions of parameters for language, models that work in the interpolation regime, they can beat the simple models, right? We know that, right? Despite things like overfitting and cursive dimensionality. So it's a bit of a conflict here, right? Because if you're a theoretical physicist who demands that your theory, that your model actually explains and doesn't just predict, then you can imagine that you might resist just outsourcing your job to an AI. But this is There is no community in physics, by the way, probably in all of science, that adheres to this philosophy more religiously than the high energy theorists, because they're the ones who want to find a simple theory for everything. Everything has to be reduced to a simple equation. And so they're the ones that are most resistive, probably, as you can see. But you can still see that there's this small community of weirdos who are quite happy and these are theoretical physicists who don't work with data. What are you going to do with machine learning models if you're not going to work with data? Well, this is a philosophical question. Yeah, so that's basically the story of deep learning in experimental and the theoretical side of physics, and where I think it's going. It's very exciting, but for some people in the community, you can imagine that it can also be quite terrifying. Not just because they're going to lose their jobs to AI, which is what everybody else is concerned about, but because it might destroy the philosophical foundations of science, which is, but then they're not the ones who are getting like Nature papers with tens of thousands of citations. So their opinion doesn't matter. Okay, that's all I have to say. Yeah, can we take questions if we have time? Any questions? Yeah?
I'll ask a question. Thank you for the talk, very interesting. One thing I maybe wanted to hear your opinion on was there is, as more and more sort of hard sciences work gets moved to things like AI work, computer programming, that sort of stuff.
Mm-hmm.
There's been sort of a question I've seen raised in a few different places where maybe the binary categories of experimental work and theoretical work is not really appropriate anymore.
Oh, yeah.
Is that something you think in the physical domain is that maybe things are starting to blur?
Oh, in physics? No, there's a pretty solid like separation between them. Like theoretical people they're not trained to do experiments. Experimentalists aren't trained to do theory. But the theoretical people do computational, work. But yeah, the roles are still pretty separated. I can't speak outside of physics, but I know for physics, yeah, there's definitely a division of labor there. Yeah. Sorry, I don't have a any deeper comment than that. Yeah.
In my previous life, I was an aerospace engineer, and the static states that you were showing in the back propagation with the positive and negatives, like the atoms changing.
Yeah.
It feels very similar to solid state physics.
No, that was solid state physics.
Yeah, but like
that.
The fact that you call it the bottle, the glass bottle, sort of, it's like.
Oh, the spin glass.
Yeah. I don't know why nobody actually is make the linkage between that and the solid state physics.
Between the spin
glass
glasses
and
and.
The back propagation that what was the one of the two? I think it was the physicist on the left hand side that you were saying that he was specialized in that.
Oh yeah, Geoffrey Hinton. Yeah.
That you said that not many people in physics use the theories, but it kind of feels like it's very similar.
Oh, like back propagation.
Cooling down of metals, basically.
Yeah. That was so. I kind of. So we have. Like to simulate things like annealing, which is when you start off at some high temperature and then the thing relaxes, and you want to see like what it freezes into. Like for annealing, which is like important for the theory of spin glasses and stuff. Yeah, I think Hopfield was the main guy. It's called Hebbian learning. So that was before backpropagation. I'm not familiar with anything that Geoffrey Hinton did that might be relevant to that. But yeah, if you know about it, we can discuss it afterwards. But yeah, I wanted to highlight Hopfield and Hopfield networks because they came from condensed matter physics. They came from magnetism, and then they turned into neural networks. But yeah, with back propagation, I think we'll have to discuss it a bit more. Yeah, I'm interested to hear your thoughts. But thank you for the question. Yep.
Did Hinton and Hopfield know each other? And if not, then how are they going to split the $1 million?
That's a good question. I actually don't know. I have no idea. I imagine, yeah, they probably would have, as people who like, yeah, Hopfield had, you know, 1 foot in computer science, so I can imagine they would have communicated. Certainly Hinton cited Hopfield a lot, of course, because he did all of his Nobel Prize work was stuff that was a continuation of Hopfield's work. So they had, you know, they were arranged in a historical sequence in terms of publications and citations. So I imagine they probably would have talked to each other, yeah. Yep.
Would you say that it's always, in a case where there's physics research and machine learning being used to progress physics, is it always physicists learning how to use these tools, or is it sometimes like also machine learning researchers kind of like dipping their toes in like physics research?
Oh, that's a fascinating question. I actually don't know, but yeah, I really don't know. Everything that I've seen is like the first thing that you said. If there's any computer scientists, machine learning people who are brave enough to work in physics, yeah, I'm sure it happens, because like there were people, I mean, like back in the 80s there were computer scientists who were working in like biology and stuff like that. Yeah, but yeah, I'll have to look. Sorry? Oh, you do, yeah. That's cool. Do you know when they went that way? How recent was that? A couple of years ago. Yeah, that's really cool. Yeah, that's all I know is what physicists are doing, unfortunately, but I'm fascinated to learn what machine learning people are doing. Yep.
Sorry, you made a distinction between simulation and making a prediction.
And a model, like a theoretical model, yeah.
So the theoretic model is the simplified version of the real world.
Yeah.
But every time you reduce that simplified model, but you also lose information along the way. So the prediction in the
Yep.
end is determined, is biased. It's not true reflection of the real world. Does that make sense? Like
Yeah.
simplify it, you keep losing information. Every time you have to reduce it down, you're taking information out. So that selection process actually reduces the integrity of the information.
Yeah, I mean, I think you just have to think about how it works with machine learning models. If you reduce the number of parameters, yeah, like a machine learning model doesn't know, like a machine learning model is in some sense like, imagine like Isaac Newton if he had a modern laboratory and could create data but had no concept of the equations and the principles that were underlying everything. Or someone, I don't know, imagine someone who was like, who didn't know physics but had access to data. That's basically what machine learning would be like. And if you get a machine learning model to come up with Newton's laws of motion or quantum physics or something purely based on matching the patterns in the experimental data, then, you know, like that's the question that I would ask. If you have a model that is really simple, it can be more powerful than a more complex model. A more complex model can be like can overfit and stuff. What's really interesting with this is if the model recognizes patterns that emerge only at a large scale but don't exist at a small scale, right? So, for example, water as a liquid has things like, you know, pressure and temperature and stuff. But if you were to look like at the individual atoms, none of those things exist. So if you had a theory that could describe the macroscopic behavior but was totally agnostic as to where it came from, like at an atomic or whatever lower level, that's when you could have a really powerful description of a system where you are extremely simplifying the system, but also extremely predictive, if that makes sense, right? So I mean, that's just an example. Like you could model all the atoms individually and make it really, really complex, as you say. That would be a simulation. But if you're interested in the large-scale properties, you could come up with something like fluid dynamics, which is a lot simpler than modeling what the atoms are doing individually, right? And that will be probably even more powerful because it's more relevant.
Ensure the integrity of the information does not lose to the prediction. So the end result reflects what you actually wanted to predict. What is the insurance process like? Ensuring that information which you try to extract and predict is not lost along the way.
You just have to compare to in physics, you compare to experiment. In machine learning, you test the model with test data to see how it works. There's no, I understand what you're saying, but there is no basic like principle that, or the more simple the picture, the more you lose information, right? So that's not like categorically true. You just have to like, you know, so yeah, my response is like, you just have to see, you have to find the right model for the right measurements, right? Find what, like decide on what particular thing you want to observe, and then come up with a model that will, you know, suit that. And it's not necessarily true that the simpler you go, the more information you'll lose.
A lot of information is redundant.
Exactly, yeah, exactly,
Maybe
yeah.
one more question,
Yep.
and then we can have follow-up discussions about, yeah.
Yeah, but that was a really great question. Thank you. Yeah.
When you were talking about, in particular, the theoretical side of things, like machine learning models potentially replacing the theoretical model, like that's the theory, and that's a bit potentially upsetting for some folk. It kind of reminded me of, I'm not like a mathematician by any stretch, but some of the controversy around like machine-generated proofs and how like they end up being lots of pages, and it gets there, but it's like people are like,
Yeah.
that doesn't feel satisfying for various philosophical reasons. Do you think?
Exactly.
Is there some parallels?
Yeah, 100%. Yeah, the more mathematically minded a physicist is, and the more obsessed they are with elegance, you know, particularly, the more they would hate the idea of AI doing something like that. Yeah, that's exactly right. Yeah, which is what you see in that in the bottom right, that community. But still, you know, you've got the heretics that are published in the 1% of papers. So yeah, there are exceptions. Okay, there was one more question. What did you take? Yep.
I was wondering, in the physics field, since the days of Hopfield network, have physicists developed new tools to solve similar problems like interacting states, like on a grid or something? Are these, and if so, have they thought about using these tools for machine learning as well?
As far as I know, they have, after Hopfield networks, that was the one thing they gave to machine learning. Everything else they stole. So nowadays, the same thing that Hopfield, you know, was trying to study, nowadays people use convolutional neural networks. So I don't think physicists, unfortunately, I'm sorry, on behalf of our community, we haven't really done anything for you guys. I'm sorry, but we just like to take your toys and play with them. That's basically, yeah. But that's, as far as I know, I could be wrong, but as far as I know, yeah, that's not kind of historically how things went. But I'm happy to be proved wrong if anybody has a better understanding of the history. Thank you. Okay, thank you.